Welcome, everyone. For today's prep, we're going to look at an example for how to calculate the volume for a solid of revolution. All right, so let's kind of recall a little bit of what we were talking about in class at the end of last class. And the situation is we're going to have a planar region. So a section of the xy axis. Usually it's going to be sitting underneath a function, extend down towards the x-axis, or maybe it'll sit in between two functions. And we're going to rotate this region around some fixed line, which we call the axis of rotation. So in this example, our axis of rotation is the x-axis here, but it doesn't have to be the x-axis. And when we rotate this section of our curve, in this case, we end up with this ribbon shape. And the problem comes down to what we're trying to answer is, how do we figure out how much space, the volume, is contained inside that surface? So we have this kind of funnel shape here, and we're trying to figure out how much volume is inside of it. And the idea is to essentially kind of slice this region up. So we're gonna do a whole bunch of perpendicular slices into this solid, and we're calling these our cross-sectional cuts. So we're gonna do a whole bunch of thin little slices. They all have a little bit of a thickness to them, but they're going to be thin. And then each of those thin little cross-sectional cuts, we're going to rotate around our axis of rotation. And what we end up with then is, in this case, is a circle, a disc. And so we can figure out the area for that disc. And it is going to have some thickness to it, but it is going to be, small. So there is a little thickness to this disc that we're going to get. And the idea is we're going to essentially transform this solid region that's contained inside this funnel into a whole bunch of tiny, really thin little discs. And we're going to figure out the volume for each of those discs and then add up the results. And that's what this integral formula does. So the area of our cross-sectional cut times dx, this is essentially giving us the volume of the disc. So it's the area times the thickness. And what the integration does is it adds all those tiny pieces up together to get the total volume. So the area times, with the thickness here, add up the results, gives us the total volume. So let's look at how to do this for this specific example. And the first step is going to be, let's draw our actual cross-section for the region. So the function here is the one we're just looking at. Below the curve, y equals e raised to the x over 2, and we're going to be looking from x equals 0 to x equals 2 here. So let's draw a cross-sectional view of what a typical washer is going to, or a disc is going to look like in this case. So first of all, let's jump over to our graph. Get out of the way. Trying out something new. So let's draw a cross-section of what a typical disc is going to look like here. So, just somewhere in the middle of your region, let's draw our cross-sectional cut. So I'm just going to throw it in. Oh, let's throw it here this time. So we're going around our x-axis. So it's always helpful to keep in mind where your axis of rotation is. So in this case, our axis of rotation is the x-axis. So it's usually helpful, sketch out the region. We're not going to be looking at super complicated curves here. So sketch out the region and just indicate where the axis of rotation is. So we're going around the x-axis here. And then we want to imagine, well, let's draw a little cross-sectional cut starting at our axis of rotation and extending through our region and then we'll stop where we, get to the end. And now we want to draw, well, what is the cross section if we imagine rotating this little line segment around our axis of rotation? What we get, or what we're going to get, is a circle. And so we're going to see, we want to calculate the area for that circle. And this line segment here is going to give us the radius. All right. And again, this little disc that we're drawing, it has a certain thickness to it, which is represented by our differential. So we're imagine having this having a thin, there is a bit of an extra dimension there. There is a thickness to it. But we're right now interested in figuring out the area. All right, so first step is draw our cross section, which we did. The next step is we want to figure out our radius. So we know our cross section is going to be a circle here. So let's figure out the radius for that. And that's where our function, that's where actually the equation of our function comes in. So our radius, in this case, we'll call it r, is just the height of our curve, which that's what y represents. Y represents height, and we know what y is equal to. So if we go back to our graph there, we have our little circular cross section here, and the radius here is just the height extending from our axis of rotation, which in this case is the x-axis, and going up to that point on the graph. So that's what y represents. Y represents the height going from our x-axis up to that point on our curve. And we know what y is equal to. All right, so once we have the radius, the next step is to figure out the area. So we know that this is a circle, and so the area of a circle is pi r squared. So let's do that. So step 3, area. And I'm probably going to overuse that switching around. So we want the area. And for the area for a circle, let's call this a of x, because the variable is going to be x. And the area for a circle is pi r squared. So we just take our value that we found, which is our function, and we're going to square that whole thing. And let's simplify this down. So when we have something being raised to a power, and then that whole thing being raised to a power, our exponent laws tell us that we multiply those exponents together. So we end up with e raised to the x. So this formula here, what it essentially is doing is it's telling us the area for any cross-sectional cut that we make. So this formula, and I'm going to use it again, get motion sickness here. What this area function does is it's telling us any cross-sectional cut that we make, it's telling us the area for the resulting circle that we get. So even if I look at x equals 2 and make my cross-sectional cut there and look at the circle there, this function is telling us the area for that bigger circle. So this function's handy. Basically, it's telling us any cross-sectional cut that we make, it's telling us the area for that specific cross-section. And so once we have our area all set up, now we're ready to actually calculate the volume here. So our volume, we'll call it V, is going to be the integral, and we kind of look at the left and the right ends for our region. So the left end of our region, The furthest kind of left we can go is at x equals 0, so that's going to be our lower bound. And then the furthest right we can go is x equals 2, so that's going to be our upper bound. And we integrate the area function we just figured out. So in this case, it's pi e to the x. So essentially what we're doing here is this pi times e to the x is giving the area for all of our little cross-sectional cuts. You can interpret dx here as the thickness of each of those little cross-sectional pieces. And what the integration is doing is it's adding all of those little cross-sectional pieces up, going from 0 to 2. So we're slicing this up into a whole bunch of little pieces. We're finding the cross-section of it, and then adding up the volume of each of those individual cross-sections to get the total volume. And now it's just a regular definite integral. So we've done the whole setup here. So now we're just ready to finish the integration. So antiderivative of pi e to the x is just going to be pi e to the x. So nice and easy there. And we're evaluating this from x equals 0 to x equals 2. So top number goes in first. We get pi e squared. And then bottom number goes in. We get pi e to the 0. And we subtract. And yeah, we can simplify. Not too bad. Pi e squared minus e to the 0 is just 1. So that just ends up being pi. And you can check. This should be a positive value. So with any of these kind of physical calculations like we're doing, like we did area should be positive. Now we're doing volume should be positive. You can check. This value here should be positive. All right, so those are the steps. Step 1, it probably helps to have a graph of your region. So, when you have the description here, try sketching the graph. And you can use, if a graph isn't given to you and you're working on homework, use an online calculator to just help you graph it. So y e to the, graph this function out. So get something like this. And then, see what x values you're given. Maybe you're given x values. In this case, we were. But in any case, draw out the region that we're considering. And then once you have the region sketched, first draw the cross-sectional cut through that region. Based on that, draw and then kind of draw out the circle and everything. Figure out the radius for your circle, which usually is going to involve the actual function. Now, we are going to see cases where we might have to modify this radius a bit, so it's not always just going to be our function here. And then once you've identified the radius, then figure out the area. And we're dealing with a circle in this case, so pi r squared. And then set up the integral. So the two shapes that we're going to see when you draw your cross section, there's going to be really two shapes. There's going to be the disk, and that's the example we just looked at. So when we have a disk, it's just a circle. And we're finding the area for that circle. And that point in the center, that's where our axis of rotation is. So imagine kind of this point here we're kind of viewing the axis of rotation kind of straight on there. So this is actually a line that's kind of pointing out the page at us. And for a disk, the area is just pi r squared. We're just dealing with a circle. Now, the other case we're going to consider is called a washer. And what a washer looks like is it's going to be kind of like a donut shape. It's going to be a circle with an inner circle removed. So the other shape is a washer. And what this is going to look like is, well, we're going to have an outer circle, and then we're going to have our center point there, That's where our axis of rotation is. And then inside we're going to have a little smaller circle. And we're removing that. So we're going to figure out the area for this kind of this donut shape where the center's kind of removed. And so the area for this is going to end up being, well, it's still going to involve area of a circle, but the idea is we're going to figure out the total area for that outer circle. We're going to figure out the area for that inner circle and then subtract it out. So this is going to be pi times the outer radius squared minus pi times the inner radius squared. And so we're going to see more examples like this in class. So we'll see you then. Bye-bye.